Hello and welcome to the second session of our Aerospace Workshop presented by SimScale in collaboration with EUROAVIA. Yes, I'm very glad to see again so many participants in our today's session. And yes, as you know, today we will discover the world of structural simulation and learn a lot about jet engine brackets. But before we actually start to talk about our today's subject, I would like again to make sure that the audio is working for everyone fine and that everyone can hear me loud and clearly. So please press the raise your hand button in the case you can hear me. Nice, I already see some hands. Great, seems like everything is working. Again, in the case, for some reasons, the audio stream should, for example, drop or the quality should become very bad during this webinar, you can also use our toll-free audio service numbers, which will allow you to listen to what I'm saying via your phone while watching the recording on your computer. And to access this, you just have to dial one of these numbers we're providing here, which are all toll-free. And after you are asked, you have to enter this access code 195.264.705, and then you will be able to listen to the audio. Great. Okay, just for general things, if you have questions or something you want to let me know very immediately, just write it into the question box or the chat box, and I will answer the question latest during the Q&A, or if it's something very urgent, I will also try to answer it immediately. Okay, great. Then let's take a look at our today's agenda. Last week we focused on wings and aerodynamics, and together we improved wing of the aircraft by adding a winglet. And a lot of you, by the way, submitted already the homework. You still have some hours, so you can still submit your homework till 12 p.m. today. In the case you should have some problems, you can also send us an email and ask for a extension of this deadline. We will decide it case by case, just to let you know. And what we will do today? Yes, first of all, we'll do a very quick wrap-up and talk about the idea of this webinar, just because a lot of people joined today for the first time. Then we will start to do a live demonstration of a structural simulation of a jet engine bracket, and you will get there for, first of all, the introduction into, let's say, the fundamental of solid mechanics. And then I will show you how to perform a structural simulation yourself. After that, I will show you your homework, and we will have time for your question, and I will try to answer all of them. Okay, great. Just about this webinar to make it very crisp. Yes, the idea of this workshop is really to provide interested young engineers and students who wants to learn about the application of simulation in aerospace industry. And the concept is that we will have every week a 1-hour online session with a live demo where you will get introduced to the fundamentals you have to know and how to use the platform. And during or the break between two sessions, which is exactly 1 week, you have time to work and submit a optional homework assignment, which is about to create a simulation on your own. And if you share this homework with us using the form, I will demonstrate this later in detail, you can qualify for a free professional training with a value of €500 as well as a certificate of participation. And just to let you know, this workshop will be recorded, so from tomorrow morning or tomorrow noon latest, you will find it on our YouTube channel, on our website, the recording of the sessions and also some other helpful resources in order to work on the homework. And therefore there is no need to start to simulate during the workshop or to take too much notes. I would suggest just focus on what I'm trying to explain you. If you have a question, ask it. And in the end, whenever you have problems or a question, use our forum. We have a dedicated section there just for this workshop series where you will get immediate help by other users and SimScale engineers. Great. Then I would say let's dive into it. And since we will again talk a lot about fundamentals today, I will try to make it very crisp, and we will start directly with our today's task. And as you know, most of, or let's say a majority of commercial aircrafts use jet engines as a propulsion system. And those jet engines are very, very large and are very heavy. And here you can see such a jet engine, which is right now in maintenance. So here you can see like the outer shell was stripped off, and now it's quite easy for the mechanics and the engineers to access all the areas of this jet engine and to check it and repair it. And if you take a more detailed look, you can see that the jet engine is in the end, it is fixed with 3 rods or 4 rods. And these rods are connected to the jet engine by dedicated brackets. And this is what you can see here. This was a red circle is. And basically, when you design, or generally when you design something for aerospace industry, all the time you want to trade off between performance, reliability, and weight. And you should know that a jet engine, it's not like a car engine, or a jet engine is nearly controlled, let's say, several times a year on a regular basis, just because you have this high requirements regarding safety. And therefore, these brackets, which are only used to connect the jet engine to the maintenance station, they are not used to connect or we use different brackets when connecting the engine to the aircraft itself. But still they use, let's say, on a regular basis, and therefore they stay on the engine all the time. And in the end, what they are doing, they are supporting the whole weight of the engine. And this engine is approximately several, I don't know, 20 or 10 tons, has a weight of nearly 10 tons. And you have just this 4 very small brackets which are supporting all the weight. And you can see how this brackets can look like. And actually what we will do today is to run a simulation and investigate if this bracket designs will last the weight of the engine. And this is very important. Even it seems to be a small part, every part in aerospace is optimized. I think this is a very good example which really underlines how engineering simulation can be used to optimize products which are used in high performance environments. And what we will do today is we want to simulate, let's say, the structural behavior of such a bracket. Here you can see 3 different designs which were created by users of a competition. And the basic setup is that if we take a look, here we have the 2 sides, and the one side is, let's say, the bolted side where we have 4 holes, and here we will fixate the bracket with that to the outer shell, outer housing of the engine itself. And this other end, which you can see more in detail on the right side, is connected in the end to your maintenance rods. And right now you have 3 designs, but in the end the loads are the same. If we want to take a, let's say, abstract physical look on this part, we have 4 fixations where we have these 4 holes, and we have 2 load cases, one horizontal load case and one vertical load case, which is in the end the weight of the engine. And what we're going to do today, we are going to simulate one of these load cases, the horizontal load cases for that case, for example, with this static fixation. And then we want to investigate, for example, if this part is bending and if it will lease, or if it's strong enough, before we start to run the actual simulation, I would like to talk a little bit with you about the theory, what means strength or stress, and how can I judge about the structural characteristics of a part. And let's go back to the basics and make a very easy example, I think, which will help you to understand a lot of options we will choose, and a lot of parameters we will define during the live demo itself. And what you can see here is a machine which I think everyone who studied mechanical engineering already saw during class. And this machine is used to characterize material probes in regards of their structural behavior. And basically it's very easy setup. You have two vices, a top and a lower vise, which are somehow, you can say, by friction connected to your sample material probe, which is a one-dimensional probe in this case, so it's symmetrical in one axis. And in the end, what we are doing now, we will stretch the sample material by moving the top and the lower vise in different directions. The top vise goes up, the lower vise goes down. And during this, we are measuring the force that is needed to get this defined strain, this elongation of the probe. We will measure how the cross-section of this probe changes. And when we have this, we can calculate the stress, because stress is nothing more than force divided by area. And the area is the cross-section area here, which is measured during this test, because it will change a little bit, but not too much. And the strain can be calculated easily, because it's in the end just the difference of the length of the probe before and after moving the vices. And if we would now start to increase the strain and take a look how stress is changing, first of all, let's say for the beginning, we will measure a curve like this, which is a straight. And this is very important, because every one of you, I think, know this effect. This is what we call elastic material behavior, which means that I have a proportional dependence between the stress and the strain, and the constant, the slope of this, is the so-called Young's modulus. So it's in the end calculated by dividing the rise through the run, which is the slope. And as long as you are in, let's say, in this particular area, as long as we stay inside this area, and let's say, for example, we go till here, and then we turn off the machine, and the top vices are not under the vices are not on the force anymore, it will go back again to this initial point. And that is, for example, how a spring is working. A spring is operated, or a spring should be operated, in the elastic material behavior of the metal it's made of. Otherwise, it will not go back into its initial condition. And let's say 99.9 technical products are operating in this elastic area, especially when they have to use a long time. But what do you think? What will happen if we increase still the strain? Then we will get a curve like this, which looks a little bit strange first of all. What is happening here? Let's take a deeper look. Here we have like a, let's say, in this area here, let me change my color, my pen. We have like here, what we can see here, it is, let's say, the interface between the elastic and the material behavior, which comes after that. Here you are like going through the border of the elastic material environment, and which results in this small fluctuation. And starting from here, it seems like you can increase your strain and your stress will not increase so much. And some point, if we still increase the strain, we get to this point. And this is the maximum stress. And if we then, and it's and between this and this point is the right side of this curved part, and the left side is called your yield strength. Makes sense, because this is exactly the strength until it starts to have plastic material behavior. And this is very important to understand. if we are here now, for example, and we will release the visors, it will not go back to this point, but maybe come back here. And what we will have then is a plastic deformation, that even if you remove the force, your part will still stay deformed. And so everything which is on the right side here is part of the plastic deformation. And so let's make it clear. This is plastic behavior. And in the end, if we put it in a nutshell, if we still increase the strain, suddenly the stress goes down. But this is not good, because just after that, your probe will break. And there are some interesting things you should keep in mind. You have the maximum stiffness in this area when you have a little bit of plastic deformation, because that will harden your material on a let's say atomic level. If you take a look at the atomic grid of the metal, and you ask yourself, why do I need it? Two reasons. First of all, this curve helps us to understand how we have to interpret the results of our simulation, or what we want to find out in the end. In the end, we want to find out if the stress in the bracket will, be bigger than your yield strength. And if that's the case, you have plastic deformation, which will have a high negative impact, especially if you come to this red area here. It will have a very bad impact on your structural stiffness. So, and the second thing is why this diagram is very helpful, or this curve, is that out of this we can get all material properties we need to define the material within SimScale or within the simulation tool. And I would say every professional vendor or reseller of metals or other materials will provide to its material this kind of curve and corresponding data. Okay, now let's take a deeper look. What does this mean? Now, if I want to describe material behavior, you should not forget this is just a one-dimensional case. But even if I go for a three-dimensional case, I can now use the information or three information to describe the material based on this curve. First of all, let's take a look at linear elastic material behavior, which is happening inside, let's say inside this blue box. There I need exactly three things to completely describe my material. First of all, the Young's modulus, which is the rise of the straight. Secondly, the Poisson's ratio. And this is a little bit more difficult to understand, but not really so hard. Just imagine, in reality, you have not a one-dimensional stress state, but a two- or three-dimensional. And just imagine, in the end, what this Poisson's ratio is expressing is how your lateral strain will change when a longitudinal strain will change. So in the end, it just says if you have compression on one side, how many elongation you will have on the other side. And the third thing is the density, which you cannot find inside this curve, as well as a Poisson's ratio, but which you know about your material. And so these three parameters, three numbers in the end, are enough to describe the full linear elastic behavior of any metal, most of the materials. But if I go to the plastic material behavior, then you can see that I now have an additional parameter, which is not a parameter, which is a stress strain curve. And in the end, we have exactly the same things like we need for linear elastic behavior. The only difference is that starting from here, we are not using any more parameters to describe the straight. We are in the end developing or providing a list with all points describing this curve numerically. And this has to be found out on an experimental basis by the manufacturer of your material. And this is, and those two let's say, two approaches, I can describe linear or either plastic material behavior. Great. Are there any questions so far regarding this? Seems to be not the case. If you have a question, just write it down. Okay, and now let's take a look at the material we want to use today. We want to use 15-5pH SS, which is a stainless steel used in aerospace industry. And we just made some research on a website of a company which is distributing this material, and we got this curve. And this is, if you take a deeper look, looking like the curves I showed you before. And in the end, this curve is describing the full material property. So if we want to fill out this material property table, which we need at least, then let's start. First of all, the Young's modulus can be calculated by dividing, just taking from this and that point and calculating the rise between this and that point. The Poisson's ratio is the only thing which is not included in this diagram, but it is added in most of the times it's added to the same page where you can find this, as well as density. And the last thing is the so-called yield stress. This is not a material parameter we need to define explicit on an explicit base, but this is the stress which is our criteria for failure of material. And let's just fill it out based on this curve. So the Young's modulus has is 200 gigapascal, the Poisson's ratio is 0.27, density is 7,833 kilogram per cubic meter, and the yield stress, or the critical stress, was 1 gigapascal, which means at the moment where the stress at any point inside our part is higher than 1 gigapascal, the part will start to deformate and will have plastic behavior. And yes, before we actually start with our live demo, I would just like to talk again just very quickly about how structural simulations are working on a technical from technical perspective, just to make sure that everybody knows what we will do in the next minutes. And I think basically you understand what our aim is. We have a load case, we know which force is acting on the bracket, how it's fixed, and we want to know, depending on the load, which stress and strains we will have in this material, in this part. And basically, to understand how finite element analyzer is working, this is how we call the technologies to simulate structural behavior. And to understand this, just let's take a look on this very easy example. Just imagine this is a simple metallic cube which is fixed on the left side, and now apply a force on the right side, and this will result in a strain. And let's just imagine I'm in this elastic material behavior. Then I can have a function which says the stiffness multiplied with the displacement is the force acting. I think a lot of you know this kind of equation. And what does it say? For very easy cases like this cube or a beam, we have analytic equations where we can use to calculate what we're interested in. Just imagine we have now another part which is with a more complex shape. What can we do here? And this is where finite element analysis starts actually. In the end, the idea of finite element analysis is that we know some general equations, this equation which is describing in a very general way, let's say the fundamental of solid mechanics, but we can only solve it and apply it for very, very easy cases. And the idea of finite element analysis, instead of solving this equation analytically, which means your result is in the end a function, we are solving it numerically, exactly like in CFD. And we again need the mesh, because we will again divide our existing body with, let's say, a force distribution into a lot of small subcells, sub volumes, which we call cells, and we will just calculate strain and stress and all the other physical quantities for the nodes of this mesh, and then we will get a discrete result. This is, for example, stress distribution. And this is very important. This meshing is the main part of creating a simulation, because here you are in the end telling the simulation tool which local precision you want. For sure, everywhere where you have a finer mesh, you will have more values, a higher density of let's say, measurement quantities, visual measurement quantities you could say, and therefore you will have a more exact result. But on the other hand, this can increase your simulation or computation capacity which is needed to solve the simulation. And in the end, you're dividing, as I mentioned, your model or your design into small elements. Basically, you can choose hexahedral, pyramid, and tetrahedral elements, but right now we are just supporting tetrahedral elements for FEA. And you can control the density, the accuracy of simulation based on the mesh. For example, if we use, instead of this, let's say, quite uniform mesh, a refined mesh, the result will also be more accurate. And you can see that here we just have the color represents the stress. And here we just have two hotspots here. And now, since we have a higher resolution, the result is looking completely different. And since a lot of people ask, what is the right mesh size? The right mesh size is at the smallest mesh size possible. So like the smallest number of cells possible, which have the same, where the results are not changing. So what you do if you want to, for example, validate a simulation, you would do a simulation where you think it makes sense and increase the mesh again and again until you see no change in results. And that means that your mesh is so fine that it's solving all physical effects. And what we will do right now is exactly running this process with SimScale. We will upload the geometry or mesh or use the geometry of this bracket, mesh it, then define the simulation itself, so define the interaction of this part between the bracket and the environment. So we will apply here the external load and the fixation, and finally we will perform a result analysis. And for sure I've prepared something again, so let's switch to the SimScale platform. As you can see, I'm still in my standard web browser. And this is a project I will share later on with you. It includes the three geometries of the brackets. And we'll open this project now. And don't forget, everything we do here is in the cloud, so nothing will get lost. And first of all, you can inspect the geometry. For example, here you can see the length of the part in different directions, so you can check if the units are still the same. So that makes sense. 0.515 meter makes sense, but if it would be like 1525, you would know you have to rescale your model. And here we can see that we have one solid, which means this model is closed, which is very important, because if it's not closed and just make our shells, it has not a volume, and therefore we cannot perform a simulation. There is a question by Pramod, and he wants to know, can the fine mesh be added only to such critical parts, or should it be added to the entire component? Pramod, that's a very good question. I think you were a little bit confused by this image I showed, because the mesh was refined everywhere, right? I will, just in 2 or 3 minutes, you will see yourself what the answer is of this question. And just to say it for sure, your aim is to have the smallest mesh possible, therefore you only refine your mesh locally there where it's necessary. But you will see what it means just in some seconds. Okay, and we will right now do the first step and create the mesh. As you know from last session, we have the 3 steps: mesh generation, simulation setup, post-processing. And so we are going from left to right, and within the steps we have this project tree guiding us from top to bottom. And we will now create a new mesh by clicking on this new mesh button, for example. And then we have to give it a name. Automatically here you can see model 1 mesh, operation 1 is fine for the mesh operation. And just to show you how you can do it also manually, instead of selecting the mesh and click new mesh, you can also click on this mesh item, new, and then you can manually define the name of the mesh, choose the geometry you want to mesh, save it, and then add a mesh generation operation. And in this case, as I mentioned, you can see it also here, for FEA we have only tetrahedral meshing right now. And we have, in the end, 4 different operation tools. First of all, the tetrahedral automatic, which we will use right now. In theory, you have to define explicit for yourself the mesh resolution for every face and every edge. And using this automatic tetrahedral mesher allows you to specify a global a mesh by 3 global parameters. That's what we will do right now. First of all, we ask which mesh order we want to simulate, and we will choose second order. You may ask yourself, what's the difference? Let me try to explain it to you in very, very simple words. Okay. Basically, what we're doing is, let's say, this is just a very, very simple example. Let's say we have a function looking like this. And this is the analytic function. And now we're gonna to approximate it numerically. Then we are creating these nodes, as you know, here. Okay, great. And now let's imagine the following. In the end, what we are doing, we are describing this curve, or instead of using a function, we describe it with discrete points. And now the question is, how do we interpolate between these points? And first order means that we have a linear first order Ritz function, so-called Ritz function, a function to interpolate between nodes. So it would look, sorry, this was not very clear, it would look like that. And as you can see, everywhere I have a high curvature, I need more elements in order to have a to recapture the curve, because right now I have like a very big error, for example, here. And in difference to that, second order elements, let's use a different color, for example, yellow. Uses a can use a kind of polynomial between the points, and therefore, like here, you get a much better representation with the same number of nodes. So, to put it in a nutshell, first order is less compute intensive with the same number of nodes, but second order you have a higher precision. And especially when you have high deformations, you should use second order, because it will have a good impact on the result quality. That's what you should keep in mind. Every time you expect you could have a lot of high deformation or plastic deformation, use second order element. Okay, I hope everybody got that. And so we will use this set automatic second order meshing. We will use a global fineness of 2 cores and use 8 cores. And then we just have to click on save and start, and our mesh will be calculated automatically in the cloud. And this will take several minutes. I've therefore prepared a project where I already finished the computation of the mesh. So let's take a look at that. This one. So you can see, again, 3 CAD models, but 1 mesh. Let's open the project. Next question is by Ben Cruz. He wants to know if we offer 2D FEA elements such CQUET4. No, Ben, we have a slightly different approach on element types than other competitors. And since we want to make it more obvious and more easy, the element selection is done by a different way, and we are not offering right now 2D FEA or 1D FEA because the request is not so big and most of customers want to do 3D FEA. But if you think that is a feature which is missing, just let us know. We have a dedicated forum section where we discuss together with our users, our engineers and our managers which kind of features should be added to SimScale in the next future. Okay, then let's see. You see it's the same geometry, the same settings, but this mesh was already finished. And you can see how it looks. And if you take a deeper look, you can see that the mesh was automatically refined here where we have high curvature or small features. And this kind of automatic meshing for sure is not very efficient because you have an intelligence behind it which detects like where we need in general let's say better meshes or finer meshes. But for let's say 80-90% of simulations, the automatic meshing is good enough to create a high quality robust mesh. And we can even take a look inside the mesh and like create a clip, for example here. And here we just define the cutting plane, let's say, by a reference point and a vector. So let's change the normal to that. Not Y, to Z, sorry. And this will take maybe 30-40 seconds, and we can take a look inside the mesh. And all these calculations are again made in the cloud. And here we go. So here you can see how the mesh was automatically refined. Okay, and I hope that answered your question, Pramod. Next question is by Laurentiu, and the question is there a maximum number of elements we should limit to if we have a more complex geometry? This is, let's say, the fundamental question of simulation. And as I mentioned, in general, a perfect simulation has as many cells as necessary and as much less cells as possible. But in general, there are two things you should consider. First of all, you should to make sure that the geometric representation is good enough, which you can is based off the size of your part. To give you an example, just imagine we would have here used very coarse meshes. Even if it would be enough to resolve the physics, if, for example, let's just mark 5 nodes here. Then it would look like that, and you would have a wrong representation. Your wrong surface would become something, let's say, sharp and edgy. And therefore, you have to make sure that your geometry is represented a good way, and also the mesh is fine enough to resolve the physics. But this is something, and as you will see with experience, in the worst case, you just have to refine the mesh if your simulation will not work. Next question is by David. David wants to know if we can perform fatigue analysis. Yes, we can. I don't know what you exactly mean with fatigue analysis. Maybe you can specify a little bit more because it's a wide range of applications, but basically we can, but we will not show it today because fatigue is not an application which is related to this bracket. But for example, if you have creep with blades or with fans, there you can, for example, it makes sense to perform fatigue analysis. Okay. Now let's switch to the next step and do first of all a quick wrap-up. So, what did I show you? We generated the mesh. So I showed you how to open up an existing project. We created together a new mesh project for tetrahedral automatic meshing. And we talked about the difference between first and second order mesh and the impact of the mesh finders. There are 2 points we cannot talk too much again today, but which you will learn if you get more familiar with simulation, I think, but just by doing, which is called CAD cleaning. It's the first thing, CAD cleaning and repair. As you can see, this is the model I meshed. Let's take a look at the CAD model. It's really like cleaned up. So We have some small faces like here, for example, which is not really good, but it's closed. First of all, the model is closed. We have no defect edges, and so it's cleaned up and simplified. And this is something you have to do in your CAD system. And the next thing we will, I think, do with what we did last week, this manual meshing is also available for FEA, but I think we will do it in the next session. There we will show you how to create the set wheel mesh manually. Anwar wants to know if we can set how many elements the mesh should contain. You mean something like a global mesh limit, right? For the not really. With this measure, you can just take a look at the final element size. But since we're working in the cloud, in the end, you don't have to care too much for the mesh size, you know, because we will not create a mesh which is too large to be performed on our machines. And this mesh, for example, has 150,000 cells, 150,000 volume elements, and 220,000 nodes. Okay, then let's finalize now let's do the next step and create a simulation based on the mesh. Therefore, we'll switch to the Simulation Designer, which is a new tab, and click on the New Simulation button here. Let's call it just maybe Simulation 1 for the first step, but if you have several simulations in one project, I would suggest to use meaningful, sensible names. And first of all, we have to decide which simulation type we want to perform. Last week we did fluid dynamics, this week we will do solid mechanics. And now you can see a lot of different options. And basically what we want to do is a static analysis, because we don't want to simulate that something is changed. We want to have a static load and a static fixation. So only these two can be important for us. And we will choose advanced because we want to be able to perform a nonlinear analysis. So click on Save, and then everything which you need will be added to the project tree. Next, we will go on from top to bottom to all red, let's say red items, and define them to make sure everything is where we need it for our simulation. So we will choose the mesh we just created, click on Save, and then our mesh is added to the 3D viewer. The next step, we will do it to reduce, let's say, our further work we have. And as you know, right now, for every phase of the CAD model, we have created an own phase in this FEA model. And this can make handling complex. And therefore, we will try to simplify our work and create so-called topology entity sets, which means we can group faces, volume, edges, and nodes into two larger groups. And this makes the handling easier. Just to give you an example, this is my part. And to make my further work easier, because maybe I want to create several simulations, I will group now all the faces which will later on have equal boundary conditions. And first of all, let's start with the restriction. The part is fixated. As I mentioned, the part is fixated to the engine with this side, and with this side it's added to the maintenance hall. And first of all, I have 4 screws here, and they are restricting the movement of the part in, let's say, 3 directions. First of all, the screws themselves here, because they're in contact through these holes, will not allow any movement in Z or X direction. What does it mean? Like, I can not move in this direction, and I can also not move in this direction. So I choose these 4 faces, click on Create Set, and call it XZ restriction. Create. Now you can see the 4 faces, and if we go on Select, they are marked. But we also have the head of the bolts. And the head of the boat that clears the selection of, let's in the end restricting any movements in Y direction. And this, therefore, let's just select the patches where there is a contact between the head of the screw and the bracket, this surface. So click on Create Set and call it Y restriction. Done. And there is just one final thing missing. If we take a deeper look, it's this lower side. And if you made a mistake, you can just, something is missing or too much, you just select the selection, delete it, select what you want to add, like here, and then you can create it again. And finally, let's create a topological entity set for the load here. Just select the surface and call it load. Fine. Now it worked, and since we have created these entity sets, we can now proceed. These two tabs, context variable contacts, are only necessary if you have an assembly made of several solid bodies. And since this is just one solid body, we don't need them. And we can proceed with the material definition. It is a little bit similar to CFD. Here again we have a material library, and basically you can describe any material based on several parameters. And in our library we have different materials like polyethylene or plastics like ABS, but we have also have metal materials like platinum, titanium, steel, but our material is not included, therefore we have to add it manually. And then let's just take a look at our slides and go a little bit back here. And here we have all we need. And basically, first of all, we will perform this analysis. So now the first thing we will do, Young's modulus, Poisson's ratio and density, we can just add it there. So let's switch. Call the material like it is defined. It's 15, 5 pH, JS. And now we can select. And if we select linear elastic, just to give you the example, then we can add the Young's modulus, 200 gigapascal, Poisson's ratio of 0.27, no creep. Creep is a different effect, and then we have to enter the density. And that's it. Apply it and everything is fine. But linear elastic means that the whole material, independent from the actual strain, will be treated like it is linear. And to make clear what this means, let's again go some slides back. This means that if we use a linear material model, even if our strain is here, you will just like continue the straight and you will get complete wrong results. So this is why you should basically have some fundamental idea about what you want to simulate before you start. Because if you use the wrong material model, your results will be bullshit to be true. I mean, that's what can happen then. But don't worry, we can also, as you know, define a plastic material behavior, and therefore we just have to change this from linear elastic to plastic. Again, enter what we need for the linear behavior. So this information will be only used to describe the linear material behavior. And then we have to specify this part of the curve. And I've prepared something I would like to show you. It's just a CSV file. and this is describing the curve. So this point is here, this point is this point, 0.005 and 1E9, and we can now upload this CSV file to describe the remaining curve. Very important here that you should not start at 0, 0, but at the yield point. So just save it. And again, sorry, just save it. And now we can use this file. So switch back here. We can upload a file, call it whatever we want. So this is a stress strain curve we will upload now. Separator is a semicolon in our case, and then just select the file, upload it, and this can take some seconds. Then you can, something did not work. And in the end, what we will do right now is uploading this CSV file, and then we just have to make sure that this is fine. Semicolon. Upload the file, and then you can take a look. Oh, we have 0, 0 here, so I uploaded the wrong file, sorry. And here we just have to, but this is not a problem at all. So I can just again open this file, remove this, save it, and then I can upload a new file. In the end, again, the same file. Yes, and now it's fine. Okay, that's it, and now we would have described theoretically plastic behavior. Finally, we have to define the boundary conditions. Initial conditions can stay as they are, and first of all we have the fixations. So we will create two constraint boundary conditions. The first one we will call y z, and the second xz, sorry, not yz, xz, and xz means that y is unconstrained while the rate is prescribed, and we will apply it on the phase set xz restriction. Then we will create a similar thing, but in this case only y is prescribed with y restriction. And finally we have to add the load, and since we have prepared everything for plastic behavior, just to type force, and then for example if we want to do the let's say the vertical load case, we will just add minus 16,680 Newton times T, and this is very important, y times T. So, and if you want to use a function, we have to add it by the way here. This time, my friends, is a pseudo time. It's not a real physical time. We use it just for one reason, because this allows us, if we save it now, no wait, we have to save it again, load type force function and then we can save it, and now everything is defined. And the only thing we have to do is just at result simulation control here, for example, we can now, and now let's get this pseudo time. Why did I use time t if it's static? In this case, if you take again a look here, it means we will ramp our force, and so we can have analyzers for different forces or different forces in one simulation. It's in the end very similar to the graph we used before. And so I will go back simulation control. And what we can do here right now, I will change the time definition. This is fine. I will use 32 cores, and I will increase the maximum runtime since the simulation can take some time. And what is very important here right now, it means that we will have 10 steps where we increase the force. And we have to just change one final thing in the numerics. This is the way how the equation is solved, and we'll change it from multi-front to months because this is more stable. Okay, and finally we will just add a result control element, and not volume calculation but solution field. We will add additional physical field, the von Mises stress, which allows us to compare stress states. And now the simulation is set up completely. We can check it, click New Run, and start it. Okay, and now this will take some time. Therefore, I prepared for sure a simulation run, including the finished simulation result. And therefore, let's just switch and make a quick wrap-up. So, what did I show you? We talked about general setup. So we choose static analyzers, we assigned the mesh, we defined topological entity sets, and we also for sure defined a material, a plastic as well as elastic one, based on our material properties we have. And yes, I also talked a little bit of numerical solver settings. This is what I would say is advanced, and we cannot talk about it too much here, but all this advanced stuff will be part of the professional training you can win for free, for example. And just to say it, I think can also add a big value to your CV, especially for freshmen who want to join in a design department. Okay, now we will go to analyze the results. And maybe at this point you will also learn a little bit about your homework, because I have prepared this simulation project here. Okay, there's the next question by Brendan. He wants to know, what is the performance of an elastic-only simulation versus the plastic simulation? Does it simulate much faster? That's a good question. Basically, for sure, it's a little bit faster. But the main reason why you should choose the right behavior is that, to be honest, if you use plastic material behavior and it's an elastic, it's okay. The other way around not. And as you saw, I think it's right, it's really related to the performance. But in general, this is just an easy example, but later on it can become very important to choose the right physics. Therefore, you should really put a focus on this. Okay, so we have the project here again. And here I created even two simulations. One with the elastic model and one with the plastic model. Everything else is the same as a mesh. And what I for sure also changed is I have a little bit smaller load for the static simulation, because otherwise for the elastic simulation, because otherwise it will become plastic. Okay, and what we can do right now, first of all, take a look at our simulation. And so we can take a look, first of all, at the, for me, the stress in the bearing bracket, and the maximum stress, as you can see. So, and then we can take a look inside this result field. So you can see from 0 to 1 we linearly increased the resulting load from 0 Newton to the maximum load of minus 16,680 Newton. Here you can see the maximum stress which is occurring, and you can see that unfortunately here between these 2 points, or even here, we are over the yield stress. So from half of this load, somewhere in this design number 1, we have plastic deformation. So it's not very nice. And now we can take even a look into this 3D simulation results. And so by default you can change this time step. For example, if we click on play here, you can now see how the stress is changing with the increasing load. And what we do right now, first of all, is go again to the latest step, the full load, and add first of all a so-called wrapper vector filter. And this filter allows you, based on the scale factor, to wrap your displacement field. That means that it shows how this part will look actually. So let's apply it and change this one, makes this one solid color. And if we now even add the opacity, we can create a nice animation. And now the last thing I do is I change the maximum value to 1E9. So my legend will be adapted here. And if we start now, you can see everywhere it becomes dark red. It's over the yield stress. And now we increase. And as you can see at here, still everything is under it. But after 0.5, after the half of the load, we get plastic deformation. And you can, by the way, even take a look inside, for example, by adding a slice filter. But the remaining steps you need, we can do this together. So right now, for example, we're looking inside here. You can see the stress distribution. But basically, you will find in the tutorial a lot of good instructions for post-processing. And therefore, I would like to close the live demonstration today. Just wrap it up. I showed you how to change the time step, which is equal to the load, how to create slices and use the wrapper vector filter. And now it's, I think, a good time to talk about your homework. And your homework will be to perform this kind of simulation yourself. And you will provide you with this project, including 3 designs, and you have to perform for each design a simulation with elastic and a simulation with plastic behavior. So in total, you create 3 meshes and 6 simulation runs. but don't worry, in the end you can copy a lot, so it will not be too much work. And yes, let's take a look. I will send you till tomorrow noon an email including all the resources you need, because again we will provide a step-by-step tutorial which you can find, if we switch to a web browser, we can find it here on our website, simscale.com/EUROAVIA. This is where you also register, by the way. And here you find already the recording of last week, and click on this tutorial button to get the step-by-step tutorial. And here you find the description. Here you can use this form to submit later on your final homework. And here, clicking on this, you can import the project including the geometries, and here you find a step-by-step instruction how to set it up, including how to analyze the results. And for sure, again, you are really free to do whatever you want. So if you want to test some more stuff, upload your own bracket design or change the load state, just feel free and play around, and we would love if you would share this then with us. So if you have a question, if you have a problem, if you want to share your results with the other participants of the course, just reply under this topic, Workshop Session 2 homework, and then we can have a nice discussion. And for sure we'll provide you also with support all the time. Okay, then we can think I'm done, and we have time now for a Q&A. First question is, I think, related to the homework by Brandon again. Could we run one of simulation with all three brackets in? Yes, you can put everything into one simulation project, so I can show it you basically. Let's switch to my let's say, what I've prepared. So this is how your final homework result should look, or what it should include at least. So if once it's loaded, you can see it here. So we have, just 1 second, we have 3 geometries, 3 meshes, and 6 simulations. Sorry, it seems to be quite slow right now. Okay, you have the 3 geometries, you will create the 3 meshes, which is just, to be honest, to click. It's this easy application. Then you can set up in the end 3 simulations, and then you can copy 1 simulation and change the material behavior. But everything is described really in detail, so don't worry. And right, so you asked a lot of questions during the session, so it seems like there are no question remained. So if nobody has any more questions, thank you very much for being here. It was a big pleasure for me. Please remind you have still time for your homework. And if you got additional questions, just write them to our forum. Thank you very much. Hope to see you next week. And by the way, keep your eyes open. We will announce something very nice related to this workshop beginning of next week. So stay tuned. Happy simulating. Have a nice week. See you soon. Bye.